So the Laplace transform, I'll call it capital X sub L, is by definition the integral of x of t e to the minus st dt. And I'm also going to mention that this is the bilinear Laplace transform. So I'm going to insert bilinear here because it's actually usually used as an integral from 0. For systems analysis, you normally assume everything's 0 at negative times, so you can start your integral at time 0. But in the bilateral transform, you start at minus infinity. And I want to use that now because that's the one that really does specialize to the Fourier transform. All right. So if you evaluate this on the j omega axis, you just set sigma equal to 0. So we'll just say sigma is set to 0. Then we get the integral from minus infinity to infinity of x of t times e to the minus j omega t dt. And that is, you may recall, the definition of the Fourier transform. So this shows you that the Laplace transform is just a generalization of the Fourier transform. And the generalization is to just replace the complex sinusoid in the kernel of the Fourier transform with a generalized complex sinusoid. So if we think of the Fourier transform as an inner product of the signal with a sinusoid at frequency omega, we're just generalizing this space of sinusoids. So we're able to project not only onto sinusoids, but onto exponentially decaying sinusoids, even exponentially growing sinusoids. So the Laplace transform has the advantage that it actually exists for growing sinusoids. So I'll just write that really quickly. We're not going to get into this. I just want you to see it and know it. I think it's just nice to have the big picture. We're not going to work with Laplace transforms much, a tiny bit at the very end of the quarter, because you really need it for virtual analog. I mean, virtual analog is just too juicy to pass up. So we'll have to see a little bit of Laplace transform activity to talk about that stuff. But really, we're not going to work, and we won't use it in the form where you ever have to evaluate an integral. You'll just be able to get the Laplace transform, go through the bilinear transform into the S-plane, get yourself a digital filter, and you're up and running. So the Laplace transform exists for growing exponentials. That's the cool thing. And it's a little tricky how you show that over the whole S-plane. It's obvious for sigma far enough to the right, because as you go far enough to the farther you go to the right, the larger sigma is, the faster this kernel decays. So eventually you'll get over there to where you can overpower any exponential growth in the signal. So as long as the kernel of the transform is decaying faster than the signal is growing, you've got an integral that exists. And I'm assuming that it doesn't blow up to the left. So maybe consider the unilateral Laplace transform for a moment. So that gives you existence to the right of some limit. And then the way you fill it in is by means of analytic continuation. And I'll just throw that out as a buzzword because it's beyond the scope of the course. But if you're mathematically curious, look up analytic continuation, and that's how you can then generalize the definition of the Laplace transform, even to where it doesn't exist in the case of this integral, but there's a unique analytic continuation to the rest of the complex plane, so you end up getting a definition of the whole S-plane anyway, except right at one point, which is the point that represents the growing exponential that you're transforming, and that's what we get that's what we call a pole. So we're going to talk about poles and zeros, so you might as well hear right now, that's what a pole looks like as a generalized complex sinusoid. A pole is, you pulse it and you get a growing exponential if it's in the right half plane. You get a decaying exponential if it's in the left half plane. And so every ringing mass spring system will give you basically one pole if it's resonating, it'll give you 2. It'll give you a complex conjugate pair of poles. And if it's just an exponential decay, it'll give you 1 pole. So that's a little bit of predictive discussion. All right, so I guess it's break time. I should take a break. But I haven't shown you the z-plane. So after the break, we'll talk about the z-plane, and then projection onto sinusoids, which is the DFT operation.